Okay, in this video we'll be going through the 2018 Scholarship Physics exam. Question 1. A railway wagon full of sand is released from a rest point at C. The wagon oscillates in a vertical curved track between A and C with simple harmonic motion with a period of 60 seconds. The effects of friction can be ignored. State the conditions that must apply for the motion to be considered simple harmonic motion. Okay, so there must be a restoring force which is proportional and in opposite direction to the displacement. Show that the maximum speed is 15.7 meters per second. Okay, so we know our Vmax is equal to the amplitude times our angular velocity. We know our amplitude is half of 300 meters, which is 150 meters. And our angular velocity is equal to 2 pi over our period. And so angular velocity is 2 pi over our 60-second period, as over here. And so plugging that in, we get 5 pi, which is indeed 15.7 meters per second. There we go. When the wagon is halfway between B and C, calculate its approximate height above B. Okay, so halfway through B and C, that's right there. Okay, so at this point, using conservation of energy, we can say that our EK at its max, EK max, which will be at point B, right? Because at point B, we have the lowest gravitational potential energy and it's moving the fastest, so we'll have the highest kinetic energy. And that's equal to our EK at point B plus our gravitational potential energy at point B also. So we can say this is our half mv max squared, where our Vmax is actually this Vmax right here. And that's equal to our half mv squared, where our V is our V at point B. And that's equal to mgh. And this h is this height right here. That is our h right there. And that h is the height that we're trying to find, right? We're trying to find how high above B is the wagon. So we can take out our mass as a common factor. The half mv max squared is equal to m half v squared plus gh. So we can cancel out our masses. The half v max squared is equal to half v squared plus gh. Now we can times both sides by 2 to get rid of our halves, and we get Vmax squared is equal to v squared plus 2gh. Okay, so at this point, we can see we know our Vmax, which is what we found in the previous question. We know g, which is just 9.81. We're trying to find h, so what we don't know is our velocity at point B. And to find the velocity, we can use our reference circle. As we know, this is in simple harmonic motion, so we can draw our reference circle right here. If we know that the wagon has moved halfway between point B and point C, we can say it's approximately right here, right, on the reference circle. So we can draw a line like this, and this is our theta. As this is the amplitude, this is 150, and the distance covered right here is 75, again, halfway between B and C. And so this will also be another 75 right there. So we can take out this right angle triangle here and redraw it. Using our trig, we can find our theta, which is equal to 1 over 3 pi. Now from that, we know our velocity at this point is equal to negative a omega sine theta. Therefore, our velocity is equal to negative 150 times our angular velocity, which again is 2 pi over 60, times sine 1 over 3 pi. And that gives us a velocity of negative 13.6 meters per second. So now that we know all our variables, we can rearrange for h. Subbing in our values, we know our Vmax is equal to 5 pi. So I'm going to put 5 pi here to keep whole values. And we can minus our negative 13.6, and that's all over our 2 times 9.81. And that gives us a height of 3.14 meters. The wagon has a small hole from which sand leaks onto the rail track at a steady rate. Sketch a height profile for the sand on the graph and explain the shape of the profile. State any assumptions you have made. Okay, so the sand profile is going to look something like this. The reason for this profile is because the speed in the middle is going to be the fastest, and so it's going to spend the least amount of time in the middle, and obviously at its max, that's when it actually stops for a moment, and so it's going to spend the most amount of time at the extremes, and so the sand is going to be a lot higher at the extremes than in the middle. So we can write that down. The highest amount of sand is at the extremes, with the least amount of sand in the middle. This is because the wagon is moving the fastest in the middle, whereas it slows down before coming to a brief stop at the extremes. Thus, the wagon spends less time in the middle compared to the extremes, therefore there will be more sand at the extremes compared to the middle. When the wagon arrives back at sea, the remaining sand is suddenly dumped from the wagon. Explain what effect this removal of mass will have on the physical parameters of the wagon's motion. Okay, so this question is fairly simple. Everything that relies on mass will be affected, such as energy and force, whereas anything else will have no effect, right? So our energies, such as our kinetic energy and our gravitational potential energy, these both have masses involved, and our force, which is F is equal to ma, or in this case is just going to be our weight force, which is F is equal to mg. That also includes mass. So those two things are going to be affected. Everything else will not change. The track A to C is an arc of a circle. By first calculating the radius of the circle, discuss whether the original assumption that this motion is simple harmonic motion is valid. Okay, so let's draw this as a circle. And this part in red is going to be our A to C, right? So that's going to be our A, and that's going to be our C. We have our B in the middle, and this is our total height of our arc, right? And so if we have the middle of the circle right here, we can draw another line across here and across here, and this is our radius, right? And this distance right here is our r minus our h. Okay, so what we are looking for is this angle right here. The reason why we're looking for this angle is because if that angle is too large, then this cannot be simple harmonic motion, as that is one of the assumptions that we make in simple harmonic motion, that it has a small release angle. And so if that angle is above, let's say 10 degrees, then we know that this cannot be simple harmonic motion. Okay, so first things first, we need to find this h value. So in order to find that, we can use, again, our conservation of energy. We know that when at the extremes, let's say point C, the wagon is going to come to a complete stop, and so the kinetic energy will be 0, and the gravitational potential energy will be max. Same with at point B, but in the opposite direction. At point B, the wagon is going to be moving the fastest, and it's at the lowest point. So it's going to have the highest kinetic energy and the lowest gravitational potential energy. Therefore, these energies must be equal, so our half mv squared must be equal to our mgh, right? This is at point B, and this is at point C. Again, we can cancel out our masses, and we get half v squared is equal to our gh, and therefore our half v squared all over our g is equal to our height. Again, our velocity at point B is our Vmax as it's moving the fastest. And as we saw before, our Vmax is 5 pi. So we can make that substitution. And we know our G is just 9.81, right? And that gives us a height of 12.58 meters. Okay, so looking at this right angle triangle here, we can draw it out as so, where this is our theta, this is our radius, this is our r minus our h, and right here, this is our 150 meters, right? That's our amplitude. So currently, we know our height, however, we don't know our radius. But what we can do is use our Pythagoras to find out r. So we know that means our r squared is equal to 150 squared plus r minus h squared. Therefore, our r squared is equal to 150 squared plus r squared minus 2rh plus h squared. And so we can cancel out our r's on both sides, and we can move this 2rh onto this side right here. So we get 2rh is equal to 150 squared plus h squared. Dividing both sides by 2h, we get r is equal to 150 squared plus our h squared, which is 12.58 squared, all over our 2h, which is 12.58. and we get a radius of 900.85 meters. There we go. And so again, looking at that triangle again, we have our theta there. This is our 900.85, and this is our 150. So again, using our trig, we can say that this angle is equal to inverse sine of 900.85 all over 150. And that gives us an angle of 9.58 degrees. And so as this angle is less than 10 degrees, just barely, the assumption that this is simple harmonic motion is valid. Okay, question 2, interference. State the conditions for stationary interference fringes to be produced by two light sources at a distance d apart. So the necessary conditions is that the two light sources must be coherent, and so the path difference between the two light sources must be constant the entire time, right? So the path difference can't change throughout their motion. And so for this to occur, they must have the same wavelength and same frequency, and they also must have the same amplitude. The reason why they must have the same amplitude is because when they interfere with each other, if the amplitudes are slightly different, then even when they go through destructive interference, not all the light is going to cancel out, right? So in order to get those dark spots, the amplitude must be the same. And also D, the separation between the two light sources, must be greater than the wavelength. Just a note on this, we can fix all of these issues by having one light source come through a double slit, which is what we usually see, right? We see parallel rays going through double slits, and we get our diffraction, like so, and we get our interference pattern. That way it fixes the amplitude problem because it's coming from one light source, therefore that also fixes the frequency and wavelength problem because, again, it's the same light source. And the path difference must be constant because, again, we're not dealing with two separate light sources. Two narrow slits separated at a distance are illuminated by a light at an incident angle of phi. Light from the two slits produce an interference pattern on the screen at a distance L away. Assume that L is much greater than D. If D is equal to 1 times 10 to the negative 4 meters, and the wavelength is 633 nanometers, calculate the smallest angle that will give you an intensity of 0 at point P on the screen, as shown in the diagram. Okay, so we know that in our standard double slit situation, we have light coming perpendicular like this, and we have our screen, and we're going to have points of maxima, right? And the angle in this scenario that we are interested in is from the central maxima to the next order, right? And from that, we get our path difference is equal to d sine theta. And we also know that our path difference for a maxima is equal to n lambda, right? For a maxima, our n needs to be a whole number of wavelengths. So this scenario is pretty similar, except that our light is not coming perpendicular. However, our math doesn't change, and also we are not looking for a maxima, we're looking for a point of 0 intensity, which is another word for minima. So we still want to use this equation where our n lambda is equal to d sine theta. However, we know that n is usually equal to a whole number for a maxima. So if we want a minima, we can change this equation to n plus half lambda is equal to d sine theta, right? If we get n.5, then we get a minima, right? So we want to find point P, and we can see point P is in the middle, and so that is where our n is equal to 0, right? That's the same situation here where our 0 order, right? So if we have our equation that we just made before, if n is equal to 0, then we have half lambda is equal to d sine theta, and therefore the inverse sine is equal to half lambda all over d is equal to our theta. Now again, I've put theta here, but we are actually dealing with phi, as we can see here. And so we can plug in our numbers, where we get half the wavelength, which is 633 times 10 to the negative 9, as we're dealing with nanometers, and our d is 1.0 times 10 to the negative 4. And that gives us an angle of 0.2 degrees. there we go. Another way to produce an interference pattern is to illuminate a small wedge-shaped air gap as shown in the diagram below. When viewed from above, alternate bright and dark fringes can be observed. The horizontal distance to the nth dark fringe is x, and at this point the thickness of the air gap is equal to t. From directly above the position marked A on the diagram, a dark fringe can be observed. Explain why this occurs. So we are looking directly over here, so this is our eyeball. Alright, we're looking directly this way. So just the gist of what is happening, we have a light ray coming down through here. And then we have total internal reflection. We learned that in level 2. And that comes up as our first ray. But some of that light is going to pass through the glass and be reflected back up as our second light ray. And that will create a path difference between the first and second rays. And therefore we get our two coherent light sources that can interfere and create an interference pattern. Okay, so at point A, the same thing is going to occur, but as you can see, at this point, right here, the two pieces of glass are touching each other. There is no air gap at point A. And so what's going to happen is the light ray is still going to come down, right? And it's going to totally internally reflect and come back up. And again, some of that light is not going to totally internally reflect, and it's going to reflect off that second piece of glass and also come straight back up. Now, because those two pieces of glass have no air gap, it's essentially the same thing as having two blocks of glass stacked on top of each other like that. And so we're going to have a light ray come down, internally reflect, and come back down and reflect off this piece of glass right there. And so those light rays are just going to be on top of each other. And so there's going to be no path difference between the two light rays. And so if there's no path difference, then they're just going to cancel each other out because the light is coherent with itself. And so we can write that in. No path difference between the two reflected rays. Therefore, there is a 180 degrees phase change due to the reflection off the glass. Thus, when the two rays superimpose, this leads to destructive interference of the rays, and thus a dark fringe is produced. Light of wavelength 550 nanometers is incident normally on an air gap of angle 3.5 times 10 to the negative 4 radians. Calculate the number of dark fringes per meter observed. So, first thing we need to know is our path difference between the two fringes is 2t, because this is 1t right here and this is a second t, so the path difference between ray 1 and ray 2 is 2t. Alright, so we can write that in. Our PD is equal to 2t, right? And therefore we know that our path difference is equal to n lambda, so n lambda is equal to 2t as well. And due to the size of the angle, we can use our small angle approximation for this, right? We can see here that this is not actually a straight line down. It's more going to be a curve due to the wedge shape. But because the angle is so small, as this is a slip of paper, like that's a slip of paper in the horizontal direction, like that's how thin it is. So that is definitely a small angle. So because of that, we can use the idea that at small angles, even though that there is going to be an arc, we can assume that instead of it being arced like this, it's just a straight line down. And so that is going to be our t, right? That's going to be this distance right there. And that is our x, which is this distance right here. And we have our theta angle right there. And so the small angle approximation is our theta is equal to t over x, right? And therefore our t is equal to theta x, right? And so we can take that, and now we know that our path difference, n lambda, is equal to 2 theta x. Now we know that our n is where we have our fringes, like that's the order of our fringes, and x is actually the per meter part. That's our distance, because if we have fringes all across here, our number of fringes per meter is going to be the total number of fringes divided by our x. So what we want is our n over x, that's our number of fringes per meter, and that's going to be equal to 2 theta all over our wavelength. And so n over x is equal to 2 times 3.5 times 10 to the negative 4 divided by our wavelength, which is 5 250 times 10 to the negative 9, again in nanometers, and that's equal to 1,273 dark fringes per meter. If the angle of the wedge is too large, no fringes are observed. Explain. Okay, so we have our equation, which we formed in the last question, where our n over x is equal to 2 theta all over our wavelength. So that means if our angle increases, our wavelength hasn't increased, it hasn't said that, nor has our x, this distance right here, right? It hasn't stated that as well. So the only thing that can increase is n, which is the number of fringes. So if our angle increases, therefore the number of fringes will also increase. So if the number of fringes increases, why can no fringes be observed? If we have our fringes like this, right, and we increase them, okay, so now we've added more fringes, and let's add some more. Right, and let's add some more. So what you'll be able to tell is if we keep doing this, and we keep adding fringes, we keep adding fringes, we keep adding fringes, there's going to be a point where they all just kind of smush into one big blob. And so if the angle is too large, the number of fringes is going to increase to a point where your eyes can't discriminate between individual fringes. And so that's why even when the angle increases, the number of fringes increases, but because there are so many of them, your eyes can't tell them apart and they just look like one big blob. Okay, question 3. Show that the force of gravitational attraction between a pair of electrons is about 10 to the power of negative 43 times the force of electrostatic repulsion. The force of electrostatic repulsion is given by that equation there, where K is Coulomb's constant and Q is the charge and R is the separation between the two electrons. So we know that our force of gravitational attraction is equal to Gm1m2 all over R squared. And as we are measuring the gravitational attraction between two electrons, m1 and m2 are going to be the same. So that means our Fg is equal to Gm squared all over R squared. Right, so now we can plug in our numbers. Now we don't know the distance separation between the two electrons. However, as you will see later on, when we compare the electrostatic repulsion and the gravitational force, these radiuses will cancel out with each other. So we can just leave it like that for now. And that top part is now equal to 5.54 times 10 to the negative 71 all over R squared. Again, we're just leaving that R squared for now. So now our force of electrostatic repulsion is equal to KQ1Q2 all over R squared, where our charges of both electrons are again the same because they're both electrons. So our equation is just KQ squared all over R squared. And so plugging in our numbers, that gives us a value of okay, so now comparing the two, we can divide one by the other. And as you can see, like I said before, when we compare them, both R's will cancel out, and we are left with 2.41 times 10 to the negative 43. And as you can see, we have our times 10 to the negative 43 right there. An experimenter is given a black box with two electrical terminals. The experimenter knows that inside the box there is exactly one inductor, one capacitor, and one resistor, but does not know the combination of parallel and series connections within the box. Using an AC generator with a variable frequency and a fixed voltage, the experimenter measures the magnitude of the AC current as a function of frequency and obtains the following graph. Assuming that the circuit elements are ideal, describe how the three components are connected. Explain your reasoning. Okay, so the inductor and capacitor must be in parallel, as we have a point on the graph where current is a minimum. Now, if the inductor and capacitor were in series with each other, when the reactance of the inductor and the capacitor are equal, we should see a max in current because they should cancel each other out. However, we see a minimum current right here. And so that tells us that the inductor and the capacitor are in parallel instead of in series. What that also tells us is that the resistor must be in series. This is because if the resistor was in parallel, this means that even though the currents from the inductor and the capacitor will cancel each other out as they're in parallel, if the resistor was in parallel, that means that still allows a pathway for the current to flow, and so current will not be a minimum. However, if resistor was in series, there is no pathway for the current to flow, so it has to drop all the way to zero. So let's write that down. This is a circuit with an inductor and capacitor in parallel and a resistor in series. At a given frequency, the current is zero. As the currents from the inductor and the capacitor are equal and opposite, they will cancel each other out. Also, as the current falls to zero, the resistor must be in series as there are no other pathways for current to travel. A resistance of 4 ohms is connected across a cell of internal resistance R as shown below. The 4 ohm resistor dissipates energy at 16 watts. The 4 ohm resistor is then replaced by a 1 ohm resistor, which also dissipates energy at 16 watts. Show that the voltage source must be 12 volts. Okay, so we know that our V is equal to IR, and therefore our current is our voltage over our resistance. So our current for when there is a 4 ohm resistor is equal to the voltage, which we don't know, and our resistance is the internal resistance, little r, plus that 4 ohm resistor. And so same thing for when there is a 1 ohm resistor, that's our voltage all over our little r plus our 1 ohm resistor, like that. Now we know that P is equal to IV, and again as B equals IR, we know our P is equal to I squared R. And so the power when there is 4 ohms is equal to I 4 squared times our resistance. So therefore our power, which is 16 watts, is equal to V squared all over R plus 4 squared times our 4 ohms of resistance. And so we can rewrite that as 4V squared all over R plus 4 squared. And again, same thing for when we have our 1 ohm resistor. That is I1 squared times our resistance, and that's equal to 1 times V squared all over R plus 1 squared. So rearranging this for our voltage, we get 16 times R plus 4 squared is equal to 4V squared. And so 4R plus 4 squared is equal to our V squared. Expanding this out, we get 4 times R squared plus 8R plus 16 is equal to V squared. And therefore, expanding that further, we get 4R squared plus 32R plus 64 is equal to V squared. Now doing the same for this, we know that this is equal to our 16 watts. And so 16 times R plus 1 squared is equal to our V squared. So 16 times R squared plus 2R plus 1 is equal to V squared. And so 16R squared plus 32R plus 16 is equal to V squared. Now, as both these equations equal V squared, we can make them equal to each other to find the value of R. So 4R squared plus 32R plus 64 is equal to 16R squared plus 32R plus 16. Now we can cancel the 32R on both sides, and we get 4R squared plus 64 is equal to 16R squared plus 16. Now minusing the 4R squared and minusing the 16, we get 12R squared is equal to 48. Therefore, our R squared is equal to 48 divided by 12. Therefore, our R squared is equal to 4 ohms. And so our R is equal to 2 ohms. That is our internal resistance. So now that we know the value of R, we can sub it back into any one of these equations. Let's put it into that equation right there. And we can find the value of our V. So we have 4 times our R squared, which is our 2 squared, plus 8 times 2 plus 16, and that's equal to V squared. Now that is equal to 144 is equal to V squared, and as you can see, our voltage is equal to 12 volts right there. There we go. Explain in detail the key underlying physics of the emission spectra of the hydrogen atom. The electron within a hydrogen atom has a restricted set of possible energy levels which it can occupy, right? That's the idea of quantized energy levels. The emission spectra of a hydrogen atom is produced when the electron within the hydrogen atom, in a gaseous state, is stimulated. When this occurs, the electron is excited to a higher energy level. Again, these energy levels are discrete. As the electron spontaneously drops back down to a lower energy level, a photon is released. This photon has an energy, and therefore frequency, due to our E is equal to hf, that is equal to the difference of energy between the energy levels, right? So if we have our energy level 2 and our energy level 1, the difference in energy between these two is going to be equal to the energy of the photon. Thus, light of discrete frequencies are produced. And again, the reason why discrete frequencies are produced is because photons can only have the energy that is the difference between the two energy levels. So if we again have our energy level 3 and then we have our 4, 4 is closer like this, only photons that have the difference in energy between these energy levels are able to be produced. So that will correlate to discrete frequencies. And so that's why you only see certain frequencies on the screen. Okay, question 4. A spring of length L and a spring constant K is cut into two parts, L1 and L2, with spring constants of K1 and K2 respectively. Show that equation there. Okay, so this scenario is very similar to when we derive the resistance equations for series and parallel, and the equations for capacitance in series and parallel. So we know that F is equal to Kx, right? And therefore X is equal to F over K. Now the total extension is going to equal to the extension of 1 plus the extension of 2. Now when I mean total extension, I mean the extension when the spring was one whole spring rather than when it's cut in two. So the extension when it's a whole spring is going to be equal to the extension of the first length plus the extension of the second length. So as we know X is equal to F over K, we know that F over K is equal to F over K1 plus F over K2. Now the reason why the force is the same is because in order for this equation to be true, the same force needs to be applied on all three scenarios. And because the force is the same on both sides, we can cancel them out. And we get 1 over K is equal to 1 over K1 plus 1 over K2. So that's meant to be a K1 right there. Okay. There we go. Consider the situation as shown above, with two springs of spring constants K1 and K2 connected together and linking masses M1 and M2, which sit on a frictionless surface. The equilibrium lengths of the springs are L1 and L2 respectively, and the center of mass of M1 lies at x1, and the center of mass of M2 lies at x2. Mass M1 is held fixed, while a force of F0 is applied on M2 in the direction of M1. Using the results of part A, show that the change of position for mass M2 is that equation there. Okay, so again, we know our F is equal to Kx, and from part A, we know our K is equal to 1 over K1 plus 1 over K2, and that is all to the inverse, right? So we know our F0 is equal to K delta x2. Plugging in this K value here, we get F0 is equal to 1 over K1 plus 1 over K2 to the minus 1 times delta x2. Now solving this bracket here for 1 over K1 plus 1 over K2, making it so both sides have the same denominator, we get K2 over K1 K2 plus K1 over K1 K2. And now because they have the same denominator, we can combine both expressions, and we get K2 plus K1 is equal to K1 K2, like so. And so we can plug that into here, and we get F0 is equal to K2 plus K1 all over K1 K2. And that again is multiplied by delta x2. and not forgetting that this is to the power of -1 as well. Okay, so now we can rewrite this expression to make it easier to rearrange, and we get F0 is equal to delta x2 all over k2 plus k1 over k1 k2. Now we can see we can multiply both sides by this right here, and we get delta x2 is equal to F0 multiplied by k2 plus k1 all over k1 k2. And there we go, we have this expression right here. So yes, both masses are now released simultaneously. The values for masses and spring constants are as shown below, and the force F0 is 2 newtons. Describe in detail the resulting motions of M1 and M2. Okay, so remembering what we did in this scenario, we have our M1, and that's connected onto a spring. We have our center point right there, and then we have a spring, and we have M2. And what we did is we pushed M1 this way and compressed the spring. And so what we did is we pushed M2 this way whilst holding M1 still. And so now what we're doing, once we have moved M2 and compressed that spring, we are now letting go of both of them at the same time. And now we can see what will happen now. And so the first thing that we need to realize is that there are no external forces. And so let's say that the center of mass is right there. As there are no external forces, what we need to recognize is that that position cannot change. The center of mass must stay in the same place, right? And that's how Newton's first law in action. As the center of mass was stationary initially, as there are no external forces, cannot just start suddenly moving. So the center of mass remains in the same spot. And so we can write that in. And so everything from this question stems from the fact that the center of mass cannot move. So if the center of mass cannot move, then when we compress M2, and we have a situation where this is M1 again, and we have this, but now M2 has now compressed and we are here. So this is right before we released. M2 is a lot closer and it's compressed. When we release M2, it's going to shoot back out that way, right? But that means that because the center of mass must remain in this position, M1 cannot move that way. Because if M1 and M2 move that way, then the center of mass must move that way. So if M2 is moving this way, then M1 must shoot off this way. And so what you'll see is when we have the spring decompressed, right? The spring is spread out like this, because they're both moving at this direction. Once the spring is super stretched, it's going to want to come back down this way. And then M1 will move here and M2 will move here and the spring will be compressed again, just like in this scenario. And then they're gonna wanna move out again. And so what you can see is we have some simple harmonic motion coming in. The springs are coming in and out and oscillating like so. And this is all because the center of mass must remain in the center. Due to this, when M2 moves, M1 has to move in the opposite direction. Thus, both M1 and M2 are in simple harmonic motion, 180 degrees out of phase, with the same period. Show that the maximum velocity reached by mass M2 is 0.4 meters per second. Okay, so breaking down this problem, we know that M2 must get its velocity from its energy, right? That's from EK. And it must get its EK from somewhere, right? And we can deduce that it gets its EK from the potential energy in the springs, right? So that's our half kx squared. Now, if we draw our situation again, we have our spring like this. And then we have M2 right here. Now, we don't know the halves of the spring, but what we do know is from previous questions is we have effectively combined these springs together. So what we can do is we can take the total energy from this half of the spring and this half of the spring, and that should equal to the EK of M1 plus the EK of M2, right? So the total potential energy in the springs must be this equation right here. So in order to find the potential energy total, we can find our total K value, where we have our KT is equal to 1 over K1 plus 1 over K2, right? And that's the inverse of that. So plugging in our numbers from here, we can say that KT is equal to 1 over K1 is 5 newtons per meter plus 1 over 10 newtons per meter, and that's the inverse of that. And we get 10 over 3 newtons per meter, right? Now from this equation, all we need to do is find our x value, and we know our F is equal to kx, so our x is equal to F over k. The force applied is given to us, which is 2 newtons, and so that's 2 all over 10 over 3. And that gives us a x value of 0.6 meters. Now with this information, we can now find our EP in the springs, which is half k, which is our 10 over 3, and times our x squared, which is 0.6, and we get an EP of 0.6 joules. Now that we have our 0.6 joules, we can use this equation here and say our 0.6 is equal to half mass of m1 times velocity of m1 squared plus half of m2 times velocity of m2 squared. Now we do not want our velocity of m1, we are only interested in the velocity of m2. So we can use our trusty conservation of momentum to sub into our conservation of energy to get rid of our v1. So we know m1 v1 is equal to m2 v2 due to the conservation of momentum. And so v1 is equal to m2 v2 all over m1. Now we know the values of m2 and m1. m1 is 2 kgs and m2 is 3 kgs. So we know that v1 is equal to 3 over 2 v2. So we can make that substitution, and we have our 0.6 is equal to half m1, which is 2 kgs, times our v1 squared, which we just found is 3 over 2 v2 squared, plus half m2, which is 3 kgs, multiplied by our v2 squared. Now we can times both sides by 2 to get rid of our halves, and we get 1.2 is equal to 2 multiplied by 3 over 2 v2 squared plus 3 times v2 squared. Now expanding this out, we get 1.2 is equal to 9 over 2 v2 squared plus 3 v2 squared. Now taking out v2 squared as a common factor, we get 1.2 is equal to v2 squared bracket 9 over 2 plus 3. Now we can divide both sides by this right here, and we get 1.2 all over 9 over 2 plus 3 is equal to v2 squared. Now we can square root both sides, and we just get our v2, and that gives us a value of v2 of 0.4 meters per second. There we go. Explain how the motion of the system will be altered if the mass of the spring was not negligible compared to m1 and m2. Okay, so there will be an increase in the period because our period is equal to 2 pi multiplied the square root of m over k. Right, so that means that period is directly proportional to the square root of the mass, and therefore if the mass increases, the period must also increase. The motion of the center of mass will remain unchanged because there are still no external forces. So another key part of this question is that the EP in the springs will remain the same, right? Because neither the K value or the distance compressed changes, and that's because EP is half kx squared, right? And because of that, because our EP is equal to the EK of 1 plus the EK of M2, right? And so that means our 0.6 is equal to half M1V1 squared plus half M2V2 squared. If this remains the same, but the mass of both M1 and M2 increases, right? If we include the mass of the springs in M1 and M2, the mass of M1 and M2 increases, therefore the velocities of M1 and M2 must decrease because we are not changing the amount of energy in the system. And so that is another thing that will be altered if the mass of the springs was included. Okay, question 5. Describe the electrical properties required for a metal to act as a dielectric. The material must be an electrical insulator and must be able to be polarized by an electric field. A capacitor containing a dielectric is initially charged and disconnected from the battery. The capacitor then has its dielectric removed as seen in the diagram above. Show that the minimum work required to remove the dielectric is that equation there, where CF is the capacitance of the capacitor with the dielectric removed, and VF is the final potential difference, and ER is the dielectric constant. Okay, so by definition, our work is equal to the change in energy, right? So our energy in this scenario is our half QV, right? So therefore, in this scenario, our work is equal to half QVF minus half QVI, right? And the reason why our charge is not labeled is because our charge does not change during this process. Only the voltage does. And so because of that, we can take out our half Q as a common factor. And we know our charge is equal to CV, right? So as our charge does not change, our capacitance initially times our voltage initially has the same charge as our capacitance finally times our voltage finally. So that means CIVI is equal to CFVF. We know the equation for our capacitance is equal to E naught ER A over D, right? But when we remove our dielectric, the dielectric constant is not needed because it's not in the capacitor. And therefore, when the dielectric is removed, so this is now our CF and this is our CI. So that means our CF is equal to E naught A over D. And because of that, we can say that CI is equal to CF multiplied by the dielectric constant. Because as you can see in both of these equations, they are the same, except CI has a dielectric constant. So if we multiply CF by the dielectric constant, we just get CI. And so plugging this into this equation here, we get CF ERVI is equal to CF VF. Now we can cancel CF on both sides and we get ERVI is equal to VF. And so our VI is equal to VF divided by ER. And so we can continue with this equation here. We know our Q is just equal to this right here. And so we can go work is equal to half CF VF bracket VF minus VI, which we know is just VF over ER. Now, as VF is on the outside anyways, we can take out these also. And so we get work is equal to half CF VF squared bracket 1 minus 1 over ER. Now we can rewrite this 1 as ER over ER because anything over itself is just 1. And so we get work is equal to half CF VF squared ER all over ER minus 1 over ER. Now as these have the same denominator, we can combine the two. So we get, and that right there is our final equation. There we go. Explain why work has to be done to remove the dielectric. Okay, so the reason why work needs to be done is because if we look at this situation here, if we imagine the dielectric is inside the capacitor, right, like this, so the dielectric is within the capacitor. When the dielectric is in the capacitor, it is polarized, meaning that the negative charge in the dielectric orientates itself towards the top or towards the positive plate of the capacitor, and the positive charge orients itself towards the negative. So because of this, there's going to be electrostatic force between the positive and negative over here and the positive and negative over here. So in order to remove the dielectric, work needs to be done to overcome this force. And so we can write that in. As the dielectric is polarized, meaning the negative charge in the dielectric orientates itself towards the positive plate and the positive charge orientates itself to the negative plate, this results in the dielectric experiencing electrostatic attraction force to the plates, Thus, work must be done to overcome this force. If the capacitor is still connected to the battery when the dielectric is removed, the energy stored in the capacitor will decrease. Despite this reduction in energy, work must still be done to withdraw the dielectric. Explain this apparent contradiction. So, as the capacitor is connected to the battery, the voltage will be constant, and therefore due to Q is equal to CV, if the voltage is constant, and the capacitance decreases because we are removing the dielectric, therefore the charge must also decrease. So as the charge decreases, the excess charge is returned back to the battery, and work must be done to send the charge into the battery. And so we can write that in. As voltage is now constant due to Q is equal to CV, as capacitance decreases due to the dielectric being removed, the charge on the plates must decrease. This excess charge is returned back into the battery, thus work must be done to send this charge back into the battery. If the charged capacitor is held just touching the surface of a liquid dielectric, the dielectric will be drawn up into the capacitor. Explain why the capacitor voltage decreases when this phenomenon takes place. Okay, so again, this is a simple case of Q is equal to CV. When we add a dielectric into the capacitance will increase, as the charge has not changed during this process, so that remains constant. Therefore, the voltage must decrease. So let's write that in. Due to Q is equal to CV, as Q is constant, but C has increased, the voltage must increase proportionally. Explain why the liquid dielectric is drawn up into the charged capacitor. Okay, so this is a very similar explanation to why it takes work to remove the dielectric. When the capacitor is held up right above the liquid dielectric, some of the field lines, the electric field lines from the capacitor, are going to touch that liquid dielectric and polarize it, right? So because a section of that liquid dielectric is now polarized, that liquid dielectric is going to experience an electrostatic attraction force to the plates, thus drawing it up into the capacitor. So if I were to draw that situation out, we have our positive right here, and we have our negative down this way, right? And we know that electric fields are slightly curved on the edges and they go straight across like this, right? And we go from positive to negative. Because at the ends of the capacitor are slightly curved, if we have our dielectric just right here, this section is the section that is going to be polarized, right? And so this section is going to be drawn up, which will cause other parts of the dielectric to fill that gap, and it's going to be a constant flow until the capacitor is full with the dielectric. So that's the situation which I just explained, visualized. And so putting it in words, a section of the capacitor's electric field will polarize the dielectric. Thus, as the dielectric is now polarized, it would experience an electrostatic attraction force, which will cause it to be drawn into the capacitor. There we go, and we're done.